రైట్ సార్ స్టార్ట్ లైవ్ కూడా స్టార్ట్ అవుతుంది.
Okay. Good evening. I welcome all the faculty members, students, and our esteemed guests to this pleasant evening. Department of Chemistry KGC Hanmakonda started MSc free coaching from since last 10 years, more than 10 years. It was successfully running, and due to the pandemic COVID-19, a new version. And before this, it was started in offline, but due to our COVID-19, it was started in online mode from CPZ 2019, and it was given a successful coaching in the case of CPZ 2019. We got good ranks, even top 10 ranks also we got, and in CPZ 2020 we got again good ranks. In below 100 we got more than 25 ranks even in CPZ 2019, and we are happy to share that we ranked first rank in CPZ 2019. In the case of 2020 CPZ 2020 we got final rank is second rank also. And most of the people, mainly our government college students, are benefited with this. And previously, JOM coaching, this JOM coaching we also started in 2019 in offline mode. And first batch we got only 3 students placed in different NITs. And whereas in JOM 2020, there are nearly 10 members placed in NITs. And also one or two members, students also bagged in seats in IITs also. And in this is the third coaching in the JOM, and we are happy to share that our KDC students also joined in NIT Warangal this last year coaching, and we are hoping this time also few people will get this one. Few people will get ranks in IITs and NITs. Okay, and with this a small introduction regarding the CPZ coaching, that is MSc Chemistry entrance coaching, and this is the 12th year I think CPZ coaching, and JOM coaching is third time. And for this I welcome our beloved principal Dr. B. Mallesham Garu, and also our principal City College principal Balabhaskar Garu. And also I invite our today's speaker, Professor Satyanarayana Garu, also my guru in Nizam College during 93-95. Heartful welcome you, sir, for this occasion. And also I welcome all the faculty members from Kakatiya Government College, Dr. B. Ramesh Garu, convener of this program, and HOD Department of Chemistry, Dr. Kandala Satyanarayana Garu, Dr. Vasam Srinivas Garu, Dr. Sumalata P. Sumalata Garu, Dr. K. Vani Garu, Ashok Elshala, myself, K. Sunita Garu, Dr. Raula Mogli Garu, Sri K. Jagadish Babu Garu. And I also welcome our faculty members, Department of Chemistry, City College, Hyderabad, Dr. Viplav Dutt Shukla, HOD, and Dr. Eluri Yadaya Garu, Dr. A. Dayanand Garu, Srimati A. Vasanta Garu, Sri Bhusi Anil Kumar Garu. And in the same time, I welcome all the students of Kakatiya Government College and also City College, Hyderabad. In addition to this, so many students are gained from different parts of the, not only Telangana, and also from the different states. And we are happy to share that some of the students, I saw one student joined from Kolkata, West Bengal. Recently, he wrote the examination also from Kolkata in JOM 2000, this coaching time, and also got good marks. And we are happy to share these things. That means our coaching is expanded, or it is gone to the all over the states in India. And last time it was from Delhi also. In CPZ coaching, there was one student joined in from Delhi. That means our coaching is getting benefit not only our Telangana and AP students, from all the states, from some of the states in the India also getting benefit. And with this small introduction, I hand over to this dais to our beloved HOD and dynamic dynamic leader, and also the idea behind this program, and also the energy behind this program also, Dr. B. Ramesh Garu, HOD, Kakatiya Government College, Hanakonda. Thank you, sir. Thank you very much.
Thank you, Ashok, sir. I think our principal is preoccupied with some call from CC, sir. So good afternoon, everyone. Respected principal of our college, Dr. K. Mallesham Garu, and principal of Government City College, Dr. Bal Bhaskar Garu. Our own colleagues, Dr. Kandala Satyanarayana, sir, Dr. Vasan Srinivas, sir, Dr. P. Sumalata, ma'am, Dr. K. Vani, ma'am, Ashok Alishala, sir, Sunita, ma'am, Dr. Rahula Mogli, sir, Jagdish, sir, and the faculty of Government City College and my own friends, Dr. Viplav Dutt Shukla, HOD of Government City College, Chemistry Department, Dr. Heluri Yadaya, sir, and Dr. A. Dayanand, who is instrumental in organizing this program, Srimati A. Vasanta, madam, Sri Busi Anil Kumar, sir, as Dr. Ashok sir told, as part of this free coaching program which we have been offering for JAM 2022, we have planned a webinar. So actually this program we have planned in the last week actually, because Professor Satyanarayana sir is preoccupied. We have slightly postponed this, and we have planned as part of the validity also. Sir, Professor Satyanarayana sir, on behalf of Department of Chemistry, Kakatiya Government College and Government City College, we wholeheartedly welcome you, sir. In spite of your busy schedule, you have accepted our invitation, and in spite of having all administrative responsibilities, you accepted to deliver a lecture on that is Spectra, that is electronic spectra of transition metal complex, which is very much useful not only for JAM students and also for PG students. That's the reason why we have shared this link to students of the PG college also, sir. Sir, once again, thank you very much, sir, Professor Satyanarayana sir, on behalf of the Department of Chemistry, Kakatiya Government College and Government City College. Now, I request Dr. Bala Bhaskar sir, Principal, Government City College, to speak few words. So, Bal Bhaskar sir.
Thank you, Ramesh Garu. Good evening to all the members. Respected Principal KGC Hanamkonda Mallesham Garu, and today's speaker, Professor S. Satyanarayana Garu, and convener of the program, Dr. B. Ramesh Garu, HOD KGC Hanamkonda, and Head Department of Chemistry, Viplav Dutt Shukla Garu, Government City College, Hyderabad, and all other members of the Chemistry Department from both the colleges. I'm very happy to present for this webinar today. First of all, I must congratulate the team who are working under the leadership of Dr. B. Ramesh for the free coaching in chemistry, giving a coaching to government college students to appear for PG entrance examinations as well the JAM of the central universities, central institutes also. So every year, so when I worked as a principal long back in 2012 at Cherial, I used to hear about this program. Of course, it is a very good program that has been offering to the students. Many of the chemistry faculty members are there behind this program to make it a success. So the fruits of the program are being taken by the students of KGC Hanamakona and also the students of the rural background today. That is the reason many of our students from the rural area are being selected in very good reputed national and international institutes for continuing their higher education in chemistry. So for which wholeheartedly I must congratulate the entire team of the chemistry department of KGC Hanamakona for taking up this program as a very good initiative. As the program was started long back, but it is sustained and it is being continued. That is a very, very important aspect because in our setup, in our government degree college setup, we are usually having most of the times, many of us are moving here and there in the name of transfers and other means. But even then, the program of KGC Hanamakona is being continuing by the Department of Chemistry. So that is a very, very great thing that we can say. So I wish all the department faculty members and congratulating and also continue the same program so that the many students are going to get benefited out of this particular program.
So thank you, sir.
Coming to the today's webinar, I must thank the today's speaker, Professor S. Satyanarayana Garu, former Vice Chancellor, Usman University, Hyderabad, from both the colleges, on behalf of KGC Hanamakona, as well on behalf of our Government City College, Hyderabad. Wholeheartedly, we thank our Professor S. Satyanarayana Garu for sparing his valuable time to share his views and knowledge over the topic called electronic spectra of transition metals. I think as our Ramesh is already spoke about the program, this particular topic is there for UG students as well for the PG students also. So definitely this topic, not only that, this topic is also going to take much weightage even in the coming entrance examinations also. The electronic spectra is one of the very, very important topic that always deals with the transitions of the electrons, the line spectra, as well band spectra in the UV as well infrared region. So definitely this is going to be a very, very important topic for all the chemistry students, not only for chemistry students, even for also physical science students, because most of the topics in this particular thing, the students needs to understand about the coupling schemes also, LS coupling, JJ coupling, and other hybridization theories. Definitely, it's a very, very good topic. It is going to take much of the weightage in the entrance examinations also. So I must congratulate the team of chemistry people from both the colleges for choosing a very good topic, which is going to be very useful to our UG and PG students. So congratulations once again. And I hope this program or this webinar is going to be more benefited to our students. Students means all our students are from the rural background also. Though the students of Hyderabad means because of the DOST, even the government city college is also getting even 90% of our admissions only from the rural background only. So therefore, most of our rural students are studying, are taking their UG programs from our government degree colleges only. So that is the reason the programs like this are going to help a lot for our students. Definitely, this is a very good topic that was chosen by the organizers. I wish you all the best for the webinar, and I also wish you all the best for your free coaching program. It is one of the very exemplary program. I used to tell about to my lecturers wherever I am, I also ask them to take this as an example and start the same kind of coaching even in other subjects like physics, mathematics, and other subjects also. In City College also, we are planning to have this kind of coaching in mathematics shortly. Everything has been prepared for it, and definitely we are going to do it shortly. So anyway, I once again congratulating the entire team of Chemistry Department of KGC Hanamakunda as well the City College, and thanking Professor Satyanarayana Garu for sparing his time. And I also thank the organizers for giving me this opportunity to see you all on this occasion. I thank one and all and wish you all the best. Thank you.
Thank you, sir. Thank you very much. So now I request Dr. Dayanand to introduce our today's research person of this online webinar on electronic spectra of transition elements. Dr. Dayanand to introduce.
Good evening,
Satyanarayana.
Principals of Government City College, Balabaskar Garu, and Principal K. Mallesham Garu from Kakatiya Government Degree College. And good evening to my supervisor and my guru, Sirasani Satyanarayana Garu, and all the distinguished professors whoever are there in this webinar, and all my faculty members and all the students. Sirasani Satyanarayana sir did his BSc, that is UG, from SRA and S College, Kottagudem, Usmania University. He did his MSc in Usmania University, Department of Chemistry, and PhD, the specialization itself is bioinorganic, where he did the title of his PhD is Interaction of Metal Ions with Purines and Pyrimidines, under the guidance of the famous scientist and Professor Taki Khan. And he did his PDF in USA, where he worked along with many famous Nobel laureates. And he had 32 years of teaching at Usmania University. That's why he got, he stresses that he went up to the highest stage in Usmania University, that is as a vice chancellor. He worked because of his teaching as well as research experience. And he had a research experience of nearly 40 years in the area of bioinorganic and inorganic chemistry. We know that nowadays bioinorganic is having more importance. That he did since for 40 years. He worked on this DNA binding studies as well as vitamin B12, as well as nowadays anti-cancer agents also he is working. He, as an administrator, he started as an administrator in 2006 as a director for admissions, Directorate of Admissions, Usmania University, and later he joined as a principal, Nizam College, Usmania University, and as a director again for CETLS, RGUKT, that is IIIT Basar. He acted as a director in 2014, and after that he went as a registrar for RGUKT. After that, he worked as vice chancellor for Usmania University, and at that time, during the time of as a VC of Usmania University, he was in charge VC for JNTU, Rayalaseema University, JNTU again, Hyderabad, JNTU, Anantapur, RGUKT, that is IIIT Basar also he was in charge, and he worked he made many developments in those areas. Especially, he had recruited 170 assistant professors. Because of those assistant professors only, the university, Usmania University, is having some professors at least, though there are many vacancies. All those 170 professors were filled only by him. And under his vice chancellorship, he made 12.4 crores, 5 crores of rupees sanctioned each engineering and technology division. That is also major, that is initiative he had taken. And he was identified, Usmania University was identified as a nodal agency for APSET, and UGC also permitted the same for the next 3 years under his guidance only. And that is about his guidance, and that is about the achievements of Sir. He is a member of Executive Council, that is Council of Science and Technology, and he worked as a member in State Council of Higher Education, and he's a committee members of many committees to look into the internal resources of the universities. He's a member of Pollution Control Board. He's a life member of Indian Science Congress. He's a life member of Indian Chemical Society. He's a chairman, managing committee, and vice president, executive board, Marif Usmani University. He's a autonomous college, UGC recognition and deemed universities all over India. He worked as a chairman for that, and he worked as a NAC peer team chairman also a number of times. He's still in that job only at present. There are many. He's a member of Royal Chemical Society, and there are many awards he got after his PhD. He got JRF, SRF from CSIR. He did his postdoctoral in the University of Mississippi. He was a postdoctoral associate in the Department of Chemistry, University of Texas. Postdoctoral associate again in 1989. Again, he went to USA. 1989 to 1993, he was postdoctoral associate. He got BSR faculty fellowship from Academy of Sciences. He's a fellow of Royal Society of Chemistry, London from 2015. And during his tenure, Usman University achieved a coveted status of university with potential for excellence, with 50 crores were sanctioned for that. Second year of his office, 113 crores to 166 crores were granted to the Usman University by UGC. There are many like this. He got nearly 35 students were awarded PhD under his guidance. He got nearly 85 papers in national as well as international journals. Okay, he's having there is a long list of his achievements. Thank you, sir, for giving me opportunity to introduce my guru and my mentor and my guide, Professor Satyanarayana Garu. Thank you very much, sir. Thank you so much.
Thank you, Dr. Dayanand. Now I welcome on behalf of Kakadiya Government College, Hanamkonda, and Government City College, Hyderabad. I cordially welcome Professor Satyanarayana, sir, to start his webinar. So welcome, sir. So please. Thank you very much, sir, once again for joining us.
I congratulate the organizers, particularly Ramesh, Dr. Ramesh and his team, and both the principals of these two colleges, and all other staff members who are involved in this JAM and CPGET and other MSc entrance examinations. And you are doing a very good service to the rural. Hello? Diana? Now?
No, sir, not audible, sir.
Sir, audible, sir. No problem.
Happen.
Audible, sir.
Sir, fine, sir. Vinpadum. Sir, Silla Jain.
Yeah.
Fine, sir.
Okay. Yeah. So I congratulate the entire team, and I also thank you, Dr. Ramesh and Dayanand, for inviting me to be speaker for this good program. Thank you. Now I'll start the electronic spectra of transition metal complexes. Okay, so now we'll start with introduction of what is spectroscopy. So you all know that spectroscopy is nothing but electromagnetic radiation, which can interact with a material sample. So some type of absorption takes place because this usual spectroscopy or electron
excuse me, sir.
spectroscopy
Sir,
comes
excuse
under. Hello.
సార్ ఈ స్లైడ్ ఓపెన్ కాలేదు సార్, ఓన్లీ మీ డెస్క్టాప్ మాత్రం ఓపెన్ అయితే స్లైడ్కి రాలేదు. మీరు
There, okay. Now.
లేదు. ఓకే సార్, నౌ ఓకే సార్.
Now okay. Okay.
ఓకే సార్.
Okay. So of course the electromagnetic spectrum involves various radiations ranging from very low energy micro radio waves to the gamma radiations. Of course, in between we'll get the visible radiations and ultraviolet radiations. Now, so just now we discussed the electromagnetic waves is nothing but the propagation of two radiations. One is the electric field vector and the magnetic field vector, which perpendicularly propagate together. Okay. So this is the way it will propagate. So the terms that are going to be used in this electron spectroscopy is wavelength, frequency, wave numbers, velocity of light, etc. So the wavelength is the distance between two crust or two trump is the wavelength. Now, so these are the various radiations and their range. For example, far ultraviolet is 10 to 200 nanometers. Near ultraviolet is 200 to 300 nanometers. Visible is 380 to 780 nanometers. So, of course, in electronic spectra, mostly we are going to talk about a visible spectroscopy, and a little bit of the ultraviolet part of the spectrum is used in the metal complexes. So metal complex are transition metal ion transitions. Now, what we are going to measure in the spectroscopy is it is energy needed for the transition of electron from the lower energy to the higher energy. That energy is equivalent to h nu. H is a Planck's constant and nu is a frequency. Then energy equal to nu can be expressed as a c by lambda. This c by lambda or hc in nu w 1 by lambda is equal to wave numbers, because when you are converting into the absorption, electron spectra is all mostly represented in terms of wave numbers because it's a big number. Okay, E equal to hc nu bar. Now, in the electronic spectra compared to the infrared radio or microwave spectroscopy, the electron spectra, you can see electron spectra, the spectrum is very broad. The reason is the electronic transitions, if you take from E0 to E1 or E1 to E2, so each electronic transition is combined with various other transitions, that is rotational and vibrational transition. Whenever electron transition takes place, along with electronic transition, you have a vibrational and rotational transition. So in between the vibrational, you can see these are the small one are the rotational transitions. From here to here is the vibrational transitions. Here to here is the electronic transitions. So because of the electronic transitions, okay. Because of the electronic, each electronic transition is, is it audible to you, everyone?
సార్ కొంచెం వాయిస్ లో ఉంది సార్, కొంచెం వాయిస్ కొంచెం లో అంటే స్పీకర్సా లేకుంటే సౌండ్ చూడండి సార్.
Now it's okay. Yeah. So now,
Okay, sir.
If you
Better.
see the electronic transition is accompanied by the vibrational and the rotational transitions, Okay. Then, so that's why if you see a spectrum, the spectrum is absorbance versus the wavelength or later wave numbers, etc. One second. Okay. So when you see the spectrum, you see it is very broad, and you can also see the shoulders. You can also see the shoulders. So these shoulders can be equivalent to this rotational, the in electron spectra, the rotational transitions also you can see here. That's why if this is a fine spectrum, and generally it looks very broad spectrum. So because of this all other transitions, electron spectra is not as sharp as other spectroscopy NMR and other things, right? So the position of the peak is explained by the lambda max. That means where the compound absorbs maximum absorbance, that is the lambda max. So the intensity of the band is the absorbance, and the molar extinction coefficient we can calculate from the absorbance. You can calculate the molar absorption coefficient, okay, or extinction coefficient. The molar extinction coefficient or absorbance versus wave numbers or wavelength, we can plot the spectrum. Now, basically you can calculate from the data available from energy of the transition. So for example, E equal to H, H is a Planck's constant, E equal to Hc by W. This is the lambda. Lambda is the wavelength where it has the lambda max of that peak. Okay, if you substitute Planck's constant and lambda max and the light velocity, okay, you can calculate the frequency here, and you can also calculate the energy like this, energy in joules, energy in calories, like this. So the simplest instrument that is used to measure the absorbance is the spectrophotometer. So simplest spectrophotometer looks like this. You have a light source and you have a lens, and the light source passes to the lens, then go to the monochromator. This monochromator, because if you see the visible light, it has a band of VIBGR, that is violet to red, various wavelengths of the light is there. So it can separate them. And if it is a scanning calorimeter, spectrophotometer, so one lowest to the highest wavelength or highest wavelength to lowest wavelength, it will just go on. If it is a single beam spectrophotometer, what we'll do is we'll set the lambda wavelength, lambda max, because that is the lambda max where the particular sample absorbs its light maximum. So this particular light here, the yellow light is passing through the sample, and it absorbs some light, and this is the incidental light. This some light is absorbed and the remaining light is transmitted. Okay, this after conversion you will get the absorbance in a digital array in a what you call recorder. So light in, light absorbed, light out, and this always you can see transmits light has less intensity than the incident light because some is absorbed. And here the path length of the cell. Normally, most of the spectrophotometers we use normally, the path length L is the path length. Path length is 1 centimeter. Okay, so this can be by using this usable spectrophotometer. So the path length L would remain constant. So you cannot say it is always constant depending upon your utility. Okay, you have different path length of the cells. You can have 10 centimeter path length cells. Of course, a separate arrangement. Many people might not have seen how to use 10 centimeter path length cell. But whereas the less 1 centimeter is more familiar in the laboratory, and in the laboratory less than 1 centimeter also, it looks like 1 centimeter path length only, but the inside, if you see, the path length will be maybe 0.5, maybe 0.2, 0.1. So higher the concentration, if you want to measure the path length controls, that's why you have to use the lower path length. And If you want to use very high concentration, one has to go to the 0.1 centimeter path length. Otherwise, the absorbance will go more than 1, etc. Very dilute solutions, if you want to measure, you have to use a path length of high, either 5 centimeters or 10 centimeters, because it all depending upon the what type of experiment you are doing. So based on that, you have to select the path length of the cell. But normally the path length is 1 centimeter, and typically the concentrations that are used are 0.001 moles of concentration. So the once you get the absorbance equal to epsilon Cl. Epsilon is the molar extinction coefficient. So from the absorbance, we can calculate epsilon values. So usually the epsilon values are for an
Sir, speak loudly, sir.
high intensity. Now, okay. Hello.
Okay, sir. Okay, sir.
Yeah. For high
Yes, sir.
intensity absorption, the concentration is, of course, epsilon values are 10^4 to 10^6. Low intensity absorptions, the concentrations are the extinction coefficient is 10^3 to 10^4. And forbidden transitions, we'll discuss what are forbidden transitions, what are more intense and low intense absorptions, etc. So forbidden transitions, the epsilon values are very, very low. So less than 10^3, sometimes 0.1, 10, etc. So the, of course, absorbance is unitless. That's why absorbance equals epsilon Cl. The epsilon can be, the units are centimeter inverse into mole inverse, we can express. Now, so when you talk about the basic spectrophotometer, so that is the UV visible spectrophotometer. There are two different lamps are there. That is the deuterium discharge tube, that is called deuterium lamp, and tungsten lamp. Deuterium lamp covers the ultraviolet region, that is 200 to 330 nanometers, whereas the tungsten lamp covers the visible region, that is 333 to 700 nanometers. Okay, of course the lamps will illuminate the entire band of the light, whether you are choosing UV light or visible light, and depending upon the range of light you use, the monochromators or gratings, okay, they gradually change, and whatever the wavelength band, it will send to the sample in terms of bands, one wavelength after the other wavelength. So then this will go through the beam splitter. So when this beam splits, and one beam will go to the sample and another beam will go to the reference, because sometimes the reference compounds will also absorb. So that has to be subtracted. So that's why the light will go into both the sample and the reference. So then it will go to the detector and it will measure the light absorbed or light transmitted. Okay, so this is the UV visual spectrophotometer, basic components. So deuterium lamp, tungsten lamp, the filters, then go to the monochromator. This monochromatic light then goes to the beam splitter and splits two. One go to the reference sample, one go to reference, the other go to the sample. So this data will be processed, photodiode, and after going to the photodiode, then it will go to the recorder, and the recorder will give the spectrum. So now we'll talk about transitions in a metal ions or transition metal complexes. Of course, when you're talking about the transition, we are talking mostly transition metal means d orbitals. Okay, the electrons partially filled d orbital electron are called the transition metal ions. So these transition metal ions contains the 5 d orbitals: dz square, dxz, dyz, dxy, dz square, dx square minus y square. The electronic spectra is absorbed. A transition by absorbing the electromagnetic radiation, that is the visible radiation of a known wavelength. Okay, so there will be a redistribution of the electrons takes place in the d orbitals, because so when you go to the next step, we see how the d orbitals are arranged. So because of the redistribution of the electrons in the d orbitals, so one of the when we are irradiating with the visible light, so the depending upon the energy difference between the two orbitals, so energy is absorbed and the electron will go to the higher energy. During this process, light energy is absorbed. So these 5 d orbitals, of course, is the basics, okay, but I'll just give because there may be some BSc students. These d orbitals in octahedral field or tetrahedral field in a square planar field, if you see, so they will be redistributed in absence of the any ligand actually, so free ion, it is all the 5 d orbitals are degenerate when metal ion approach, ligands approach the metal ion, depending upon its geometry, how many ligands are approaching, what type of complex it is formed, octahedral or tetrahedral. So then in a octahedral field, these orbitals are split into two groups, triplet, that T2G, dx, 3 orbital dxy, dyz, dxc will go to the lower energy, and dx square minus y square and dz square will go to the higher energy. Whereas the tetrahedral, it is reverse because of the geometry, the approach of the ligands along the axis. Okay, we are not discussing detail, but here dx square minus y square and dz square, that is the two set of orbitals are the lower energy, and T2, that is the dxy, dyz and dxz are the higher energy. So in free ion means, I think when all the orbitals are degenerate, you cannot expect any transitions, right? So this ion should be occupied with the aqueous water or some other chloride, some ligands. It will be split into different, then the transitions will take place from lower energy orbitals to the higher energy orbitals. Now, so if you see the electron configuration of these various electrons in d orbitals, for example, so if titanium 3 plus Pc, it is a d1 configuration, only one electron, so it is only high spin state. The d2 titanium 2 plus, it is also high spin state. High spin in sense all the spins are free, that means they are not paired up. As long as possible, they are unpaired electrons. Vanadium 2 plus d3 also unpaired. From d4 to d7, we can see two types of configuration, low spin and high spin. Okay, you can see here chromium 3 plus, that is 2 plus, it is a d4 system. So you have these 4 electrons are unpaired, this is the low spin, and one is a pair, this is this is high spin, this is low spin. Similarly, manganese 2 plus, iron 3 plus, d5 system, you can see high spin with all 5 electrons unpaired, whereas only two pairs and one electron, it is low spin. Like that, you can see high spin, low spin, depending upon the possibility. So this high spin and low spin is because of the ligands that are binding to the metal ion. So they influence the energy difference between the two levels of the T2G and EZ in octahedral system. So now, crystal splitting energy in octahedral configuration. If you see T2G EZ, so when they distribute these electrons, so the net energy of configuration relative to the average energy of the orbitals can be calculated. Okay, so depending on the number of electrons occupied in the T2Z or EZ, and it also depends upon the type of ligand that is coordinating. So based on that, there is a pairing, that means low spin. There is a no pairing, that is a high spin. Okay, so in weak field ligands, what will happen is delta is less than P. So then when delta is less, all the electrons will be try to be unpaired. Whereas in strong field ligands, when delta is greater than pairing energy, then what will happen? Delta is very high that time. So most of the electrons try to be in the lower energy, so pairing takes place. So like that. So now titanium H2O 6 times 3 plus. This is a system having D1 system, only one electron. So because of the 6 water molecules, it will split into is the octahedral molecule. So you have a T2G and EZ. The electron is in the EZ. So when you energy, visible light is passed through the sample, okay, this aqua complex, then some energy is absorbed around 5-10 nanometers. Then one of the electron in the ground state will go to the excited state during this process. So if you record, you will get a spectrum, broad spectrum like this. So similarly, what I shown there. Now, this is the D1 configuration, and this is D9 configuration. D1 or D9, there is only one electron, unpaired electron. Okay, the transition that takes place is only one electron can go from T to G EZ or T to G EZ. Both are. Now, so delta zero, that means the splitting energy will depend upon various number of factors. One is the size and the charge of the metal ion. Second is the nature of ligands involved in the bonding with the metal ion, and the nature of the orbitals. Because when you go to the orbital, it may be 3D or 4D or 5D. Okay, so when you look at the splitting delta zero energies, if you see 4D is 50% larger than 3D. Similarly, 5D has 25% larger than 4D. So the splitting is more in 5D compared to 4D, and fisting is more in 4D compared to 3D orbitals. This all distribution of the electrons I have shown here. Okay. Now, so before going to the interpretation of the electron spectra, one of the important term what we are using here is the term symbols. It is a spectroscopic term, okay, to explain the or to label the various energy levels. Okay, so it all depends upon the electronic configuration or electrons distributed in the d orbital. So the simplest principle what we are using to calculate the term symbol is SLJ. S is the spin multiplicity. L is the orbital angular momentum. J is the total angular momentum. So these can be calculated. L values I'll show you later. So L values well equal to 0, it is S. Okay. L is equal to P. 1 it is P. L is equal to 2 it is D. L is equal to 3 it is F. Similarly, the J values, okay, total spin of all the electrons. Okay, for example, only one electron spin is up, 2 unpaired electrons are there, you can have plus of and plus of 1. Similarly, like that, number of electrons into this one. So J values are L plus S. L is this orbital momentum, orbital angular momentum, and S is spin of the electrons. So J values are L plus S to L minus S. L plus S, L plus S minus 1, L plus S minus 2, lowest is L minus S. So by substituting, you will get the J value. So you have to calculate L value, you have to calculate S value, you have to calculate J value. Then based on the rules, you can get the ground state term symbol. That means from that ground state, that level only, the electron will be the transferred and excited. So the ground state term symbol is 1, which the lowest energy level in this. This is calculated from the Russell's LS coupling, so Russell's standard coupling. For D1 configuration, if you see, ML value is 6A, but D orbital, it can be plus 2, plus 1, G minus 1, minus 2. So if D1 configuration, so ML is in 2, okay. total angular momentum L equal to sum of ML values. So since there is only one electron in the +2, the sum of L will be here, okay, 2 only. L equal to 0, I already told you, labels. Okay, L equal to 0, label S, L is equal to 1, P. So sum of the MS values, total spin of electrons, okay, L value here is 2, then you will get the D, 3, you will get the F, something like that. For D1, S is equal to 1 by 2, spin multiplicity is 2S plus 1. If you substitute half here, 2 into S plus half plus 1, this is 2. Spin multiplicity is 2 here. J value, what we will get is L plus S2, L minus S. So J is L is 2, 2 plus half to 2 minus half. So total you can get all the J values 5 by 2, 1 by 2, 3 by 2. So the term symbol here is SLJ. S is the spin multiplicity is 2 because spin is half, and D because L is equal to 2. So D is, this is D, okay, label is D, and J value is 1 by 2, half, because the rules also I'll tell you. When the number of electrons in the d orbitals are less than half filled, lowest J value we will take for the lowest energy term, ground state term symbol. Ground state term symbol in the sense that is the lowest energy. There are various terms are possible, but we are talking only in the strong field model and weak field model. If you go on seeing, so you can get various ground state terms you will get. In addition to that, there are several micro terms also will get, but we will take here lowest energy ground state term, that is the SL will be the same, and generally the J values, depending upon the various J values, we can have several ground state term symbols. So, but among them, depending upon the number of electrons in the d orbitals, whether it is the more than half filled or less than half filled, we will choose the J value. So here, okay. Now, here if you see here, electronic configuration, there are how many carbon? 1s2, 2s2, 2p2. So there are 2 unpaired electrons in the carbon in 2p level. So the 2s plus 1 is the spin is 1 plus of s equal to 1, 2 into 1 into plus 3. Spin multiplicity is 3. This is s is 3, SLJ, and J values are L plus S2, L minus S. Okay. L value we have seen because plus of 0 minus 1. So L is 1. So 1 plus 1 to L plus S2, L minus 1 you will have. J value is 2, 1, 0. Okay. So J equal to 0. So SLJ 3P0. The ground state term symbol for carbon is triplet P0. So because less than half fill, so lowest J value is 0. So the ground state term symbol for carbon will give you as a 3P0. Others we can also get 1D, 1S also we will get, okay, when we are go on writing all these things. So hence the 3P is ground state term order for ground state term symbol is because when you are selecting the ground state term symbol, again you have to say the highest spin multiplicity. So 1D and 1S also will get. The highest spin multiplicity is 3p, and among the highest spin multiplicity 3p, there are J values. You have 2, 1J. Sorry, there. But since it is less than half filled, you have to select the lowest J value. So though you have in 3p term symbol triplet P, 3p0, 3p1, 3p2. So 0 is the lowest energy. So this can split into 3p0, 3p1, 3p2, but the lowest is the 3p0. So that is the ground state term symbol. So the rules that what we are used in this for calculating the term symbol is the maximum multiplicity for a given electron, the term with the greatest multiplicity lies the lowest in energy. That's why we have taken in carbon triplet P, because that is the greatest multiplicity, though you have other multiplicity also. That's a 3p you have taken, not 1d and 1s. And another rule is the terms have same multiplicity. The one with the greatest, the greater the value is the lowest energy. Same multiplicity, but whenever the J value is low, that is the lowest energy. And for electron subcells that are less than half filled, if it is less than half filled, lower the values, lowest energy we are taking now. So now we have taken a metal ions, we have taken simply, but the metal ions and other free ions we have taken. Actually, system, we are when you are talking about the transitions, it is not that free ion, it is always associated with some ligand. So because of that, crystal field splitting takes place, and there is a weak field approach and there is a strong field approach. Weak field approach in the sense when the electronic repulsions are dominant than the crystal field splitting, okay, and repulsions are more, what will happen is it will be always in a weak field mode, mostly spin, high spin complexes will get. In the strong field approach means the crystal field splitting is dominant than the electron repulsions or electron interactions. So then you will always get the low spin complexes. Now, if you see here, the possible arrangement for an electron or for a D2 complex, titanium 3 plus, if you take D2 and vanadium 3 plus also D2. So as for the term symbols, you calculate, because the 3T, because there are 3 triplet T's we will get, okay. So that's why we have taken 3 triplet energy levels. One is the triplet A, okay. The electron transitions takes place from, because it is a triplet state. One electron goes here, it is still triplet. One electron goes in here, x square minus y square, dg square and dx square minus square. One electron goes to dg square, still we will get the triplet state. One electron goes to the dg square, still we will get a triplet state. So you can, the transition can take one triplet state to another triplet state, a triplet state and triplet A. I think so, right? We already discussed the ground state term of a maximum multiplicity. We take S. If two terms have same S, highest value of L will take, okay, and less than half filled, lowest value of J will take, and more than half filled, highest value of J will take. That is the lower energy. Now, these are the various ground state labels, SP we discussed. Corresponding to that octahedral field, we will get for S ground state, we will get A1, P ground state, we will get a T1 label, D ground state, you will get E plus T2, F ground state, just now we have seen A2, T1, T2, G ground state, we will get A1, E, T1, T2. These are the ground state term symbol, and H, you will get E plus T21 plus Q2. They are the ground state electronic configuration and their counterparts in octahedral field. Of course, all these we need character table to know everything, each what is A1, what is T, what is E. So you need the group theory knowledge and character tables. So from that you have reducible, irreducible representations finally in octahedral field. So what you will get, you will know. For the time being, you can just remember this basically from the ground state term symbol, the SLJ rule, okay, and further extension. Now, if you see the in a triplet electronic state for the transitions that takes place is 3F. Yeah. Now you can see here for a atomic state considering 3F and 3P states from the table. So the transitions that are taking place, because always you have to see, we will also discuss this selection rules. The transitions that are possible only, that's why only these states were taken. There are so many other ground state term symbols. Only these transitions, these we have taken for each 3F or 3P, because any transition that takes place without change in the spin of an electron, that means spin multiplicity, change in the spin multiplicity is forbidden. Only whenever electron transition takes place, there should not be change of spin of an electron. That means if it a ground state is triplet state, excited state must be triplet state. Okay, that's why triplet 3T12, it will go to triplet 3 triplet T2, but if there is one doublet T2, it will not go. That's why the electron transition, there are 3 transitions possible: triplet T12, triplet T2, triplet T12, triplet A2, triplet T12, triplet T1. So these are the transitions that are possible if these two term symbols. So these can be represented by these electronic transitions can be represented by usually Argel diagram. Okay, the simplest Argel diagram for electrons having D1 and D6 and D4 and D9. So there is only one transition, D1 level or D6 or D4 or D9. Only one transition possible. So D1, D6 octahedral and D4, D9 tetrahedral will have similar type. Only thing is, in octahedral we'll use G because there is center of symmetry. In tetrahedral we don't use G because there is no center of symmetry, centrosymmetry, right? So here easy to 2Tg in tetrahedral and octahedral, tetrahedral D1, D6 and octahedral D4, D9. So this shows all other electrons. Other than this, you can say the remaining electron D2, D7, D3, D8. So they will have, all these will have minimum three transitions, 1, 2, 3 transitions that are possible. This can be shown by simply by an Argel diagram for D1, D9, D4, D7, and similarly D2, D7, D3, D8, D2, D7, and D3, D9, D8 systems. Now, if you see the energy level diagram for a D2 configuration, just now I told you there are 3 transitions are possible for a D2 configuration. One is here to here, low energy, little higher energy. This is further higher energy. So triplet T1G to triplet T2G, triplet T1G. If you see this, so here we can see only 2 transitions. Okay, the spectrum actually one may be obscured. This the T1G to T2G. These 2 maybe, this is 3 T1G to 3 T1G, right? Higher energy, and this is next higher energy. This is the lower energy is obscured here. So you can, though it is 3 possible in the spectrum, we can see clearly 2 transitions. So then similarly, nickel H2O 6 times and nickel ammonium 6 times. The energy diagram for D8 configuration in octahedral field. So again here you can see 3 clear transitions, the transitions which are possible here from the diagram. From when you record the spectrum, also we'll see the 3 transitions: triplet A to G to triplet T to G, triplet A to G to triplet T1G, and triplet A to G to triplet T1G. It is from P. These are from D. Right now, so when you see any spectroscopy, you always have some selection rules, because the selection rules tells that what type of transition is possible, what type of transition is not possible. So one of the first selection rule in the electron spectra of transition elements is, so delta L equal to plus or minus 1 is allowed. That means S orbital to P orbital, the L values, one is S is 0, P L is equal to 1. So delta L is 1. Okay. Similarly, P to D, delta L is 2 and 3. Okay. 1 and 2. So that's why difference is 1. So delta L plus or minus 1 is allowed transition. So that's why we are talking about the DD transitions in transition metal and absorption spectroscopy. What we'll see is the DD transition. So DD transition means S is equal to 0, P equal S, P, D, D equal to 2. So the DD transition means the transition is taken from one d orbital to the other d orbital. That is, delta L is not plus or minus 1. Delta L is equal to 0. That's why, though we are talking about electronic spectra of the metal complex of the transition metals, the DD transitions are forbidden. When DD transitions are forbidden means the transitions are not allowed transitions, but still we are getting the spectra. Then we'll see. So what are the allowed transitions? One is S orbital to P orbital. Electron goes from S to P is allowed. Electron goes from P to D is allowed, and electron goes from D to F is allowed. Electron between P and F and F, D and D are not allowed transition because the first selection rule, orbital selection delta L plus or minus 1 is not fulfilled when electron transition takes place between DD transitions. Okay. Spin selection rule. So there is no change in the spin of an electron. When a transition takes place from here to here, for example, so both are spin up. So after transition also they should be spin up. They should not change the spin. So like this, for example, in 3T, 2 electrons are spin off. If one, while when it absorbs the energy and transition takes place, if this electron changes the spin in excited state, so this is a singlet state, this will become a triplet state. That's why this transition is not possible. Whereas here it is a triplet state, the excited state is a triplet state. That's why this transition is possible. So spin allowed transitions only when electronic transition takes place. There should not be change in the spin of electron. If there is a change of the spin of the electron, that transition is a forbidden transition, not allowed transition. This is spin selection rule. Then, so if your molecule, your complex, right, your system has a center of symmetry. So you have then G and U terms are there, Gerade and unigerade. G to G transition is forbidden. G to G means T to G to EZ is forbidden because octahedral molecules complexes are center of symmetry. So G to G is forbidden and U to U are forbidden. But only allowed transitions are G to U or U to G. So that means, so gerade to ungerade or ungerade to gerade are possible. But in most of the transition metal complexes, when you're talking octahedral complex, you are labeling that the transition is taking from 2TG to EZ, right? So this is a forbidden transition. Whereas, but still transitions are taking place and absorption is taking place. So we'll see what are the limitations and why it is taking place. Other thing, delta L is not forbidden. Example, titanium H2O 6 times 2 plus DD transitions are allowed because, okay, delta L is not one, orbital selection rule is not obeying. T to G is same symmetry, hence laboratory forbidden. So these DD transitions are not allowed because of the two reasons. One is orbital selection rule, another is gerade to ungerade. Spin selection we are not tracking because spin selection may take place. So only one is allowed here. Orbital selection rule is not permitting this transition out of the three, and the Laporte forbidden rule is also not allowing T to the TSU, but spin multiplicity rule is allowing this particular transition. So the T to G to EZ, that is the Laporte forbidden rule, this can be circumvented because of many reasons. The reasons are, in an octahedral symmetry, if all the ligands are not equal, So then what will happen? The center of symmetry is removed slightly. That's why this particular transition is not purely G and G. Okay, it is a D. It is not purely D and D orbital. There is a S or P orbital mixing takes place in the excited state. That's why this is allowed, because the center of symmetry is slightly removed, because all the electrons are, all the ligands coordinating to the not in titanium H2O 6 times. There are many octahedral complexes. Some 4 ligands are same, 2 ligands may be different, 5 ligands are same, 1 ligand may be different. And another rule is, when molecule is vibrating, okay, this center of symmetry is removed temporarily. That is known as Vibranic coupling. So the DD transitions are allowed because of the Vibranic coupling. Okay, so where coupling of electrons and vibranic levels are called Vibranic coupling. So when transitions are taking place, the coupling of electrons and vibration levels, vibranic levels will interact. That will also remove slightly center of symmetry. Because of that, though the octahedral complexes, the transitions between T to G easy or Laporte forbidden, they are allowed transitions because of the center of symmetry is slightly removed. One, because of the if all ligands are not same, or if all ligands are same also, the center of symmetry is slightly removed because of the Vibranic coupling. Whereas for complex of lower symmetry, that means when compared to the octahedral complex, tetrahedral complex is lower symmetry. So in tetrahedral complexes, there is no center of symmetry. That's why the T2 to E, we will not call it as a T2G to EZ, the E to T2 we'll call. So this transition is possible. So they have no center of inversion. Electron transitions are more intense. That's why when you compare with a similar type of ligands, a tetrahedral complex and an octahedral complex, if you take the tetrahedral complexes, the signal is more intense than the octahedral complex, because octahedral complexes are centrosemic. That's why the T2G to EGT transitions are forbidden, slightly relaxed because of the Vibranic coupling. Whereas in tetrahedral complexes, there is no center of symmetry. The T2 to E or E to T transitions are fully allowed. That's why the probability of transitions are more and the intensity of the signal will be more. So if you take an example of a spectra of octahedral complex COH2O 6 times 2 plus and a spectra of COH2O 6 times. One is COCl4 2 minus, it is a tetrahedral. COH2O 6 times is a octahedral. So you see here cobalt complex, both are cobalt 2 plus complexes. This octahedral tetrahedral complex will give a more intense signal around 700 nanometers, whereas the signal is very weak signal, and this is dark blue. Okay, the signal is the spectra DD band is this is weaker and pink in color, and this is blue in color. That's why this complex actually COCl4 is added in the silica gel. Silica gel, you know, it is a drying agent. So when silica gel is dry, what will happen in desiccators, etc. we use? So when it is dry, it is blue in color, right? So after sometimes when it will absorb moisture, the COCl4 converts into COH2O 6 times. That means the COCl4 which is there in the silica gel will convert into an octahedral COH2O 6 times. That's why the blue color of the silica gel converts into the pink color. That means, so this complete the absorption capacity of silica gel is gone now. So the change tells that whether the change is because the complex which we added moved from tetrahedral to octahedral. That means what we discussed, a octahedral complex is weak transition, whereas a tetrahedral complex is a strong absorption, more intense absorption takes place. Similarly, if you see an I spin D5 complexes, if you see the DD transitions, as I told you, DD transitions are forbidden by all three selection rules in D5 complexes, because the transition that are taking place is DD, because plus or minus L is 0. That's why it is forbidden. Then all in D5, all the electrons are unpaired electrons. Okay, T to Z we have 3, EZ we have 2 electrons. Any transition from T to Z EZ makes the one of the electron, it changes the spin and it will become, it has to change the spin, because otherwise it will not stay there. Spin pairing takes place. Because of that, what will happen here? 5 unpaired electrons, spin multiple is 6. Here 4 unpaired electrons, 3 unpaired electrons, spin multiplicity is 4. That means there is a change. That means because of
Sir, sir, meet lo unnaru.
yeah.
Yeah, sir.
Okay, yeah. So the first selection rule, it is forbidden because DD transition is not allowed. And second selection rule, multiplicity, spin multiplicity, this is also forbidden because there is a change in the spin multiplicity. Okay. Now, but still why the transition takes place, we'll discuss. That's why the transitions which are taking place here, move the window. Okay, so we'll get several weak bands we'll get in a manganese 5 hexa aqua complexes. I mean 2 plus H2O 6 times, we'll get very weak bands. But manganese, you all know, we'll discuss later that thing. Okay, so because these are forbidden transitions, that's why the transistors are very weak, and we don't get a very good spectrum for the manganese 5. So which selection rules forbid DD transition square planar complexes? In square planar complex also centrosymmetric, the Laporte forbidden rule, delta L rule, because DD transitions, that's why these two are forbidden. So what order should be expected for the intensity of the DD transitions of these complexes? These are all octahedral complex, MCl6 2 minus, and trans MH2O4 times Cl2, and cis MH2O4 times. This is more centrosymmetric compared to these two. Among these two, cis and trans is more centrosymmetric than cis. That's why, so when the center of symmetry is removed, that transition is more probable. Okay, so more intense transition is with the cis complex, then followed by the trans complex, then followed by the purely octahedral MCl6 complex. Because so this is forbidden transition, this is also forbidden, this is compared to completely forbidden, this is compared to this less forbidden, compared to this less forbidden. That's why this is more intense, then followed by this less intense, then this is less intense, this order. Now this already I discussed it. So the absorption spectra of cis complex and trans complex, just now I told, no, cis and trans I have seen COEN twice F2, trans COEN twice F2. So if you see here, A is a cis complex, B is a trans complex. So you see the absorption spectra of trans and absorption spectra of cis. The absorption spectra of cis is more intense because cis complex is a little more, trans complex is more centrosymmetric than the cis complex. So various types of transitions, if you see spin forbidden transitions, the extinction coefficients are less than 1. spin allowed Laporte permanent transitions 1 to 10. Spin allowed Laporte allowed transitions are 10 to the power 3 to 10 to the power 4 epsilon values, and charge transfer transitions are the highest, more intense, that is 10,000, 10 lakhs to 50,000 to 10 lakhs, something like that. So absorption epsilon, of course, this all we know. So the electron spectra of complexes with organic ligands will give more intense bands than absorption spectra of complexes with inorganic ligands, because in organic ligands mostly we also have some of the pi bonds are available, pi transitions are available, and lowest energy pi star orbitals, empty pi star orbitals are available. Then metal to that pi star is a yellow transitions, which because of that more intense colors are observed. So more covalency, intensity is more. Band intensity are more in spectra of asymmetric. We discussed it. Band intensity are more for non-centrosymmetric molecules complexes than the centrosymmetric complexes. Now, so ML4 tetrahedral is more intense. Trans isomer is less intense. Cis isomer is more intense. We discussed with the examples, all these. Octahedral is less intense, tetrahedral is more intense. In octahedral, trans is less intense and cis is more intense, because of these are all because of the centrosymmetric, eccentric or non-centrosymmetric. Now, so you all know that potassium permanganate gives a very intense purple solution. So this is potassium permanganate in manganese is +7. There is no d electrons. DD transitions are not possible there. There is no d electrons at all. But still, so the electron spectra of potassium permanganate, that is permanganate ion, if you see, you will get a purple color solution. That means it is absorbing the light. The reason here is, here the transition is taking place not between manganese and manganese. The transition is taking place between the non-bonding electrons on the oxygen to the empty d orbitals, low-lying orbitals and oxygen to the high empty orbitals of manganese. So that is the charge transfer transition. We will discuss little more. Even in the magnesium, zinc sulfide is colored. Hello. Zinc sulfide is colored, but magnesium does not have partially filled DR, because for electronic transition to take place in transition metals, either you have a you must have a partially filled d electrons. Completely empty d orbitals, completely filled d orbitals cannot take place any transition. So magnesium, the completely no electrons is manganese, completely filled is mercury. Mercury is a sulfide is also colored. This is also because of the transition between the s electrons to the filled mercury to the empty s orbitals. Here, filled oxygen orbital to the empty manganese. Ligand to metal, we can say here metal to ligand. So these are called charge transfer bands. The charge transfer bands are more intense, more than 1,000 times more intense than the DD transitions. So DD transitions, as I told you, they are not allowed, but they are forbidden because of certain Vibranic coupling and other things. Weak transitions are possible. So the metal ligand transitions. So all ligands possess sigma star orbitals, pi star orbitals, and sometimes non-bonding electrons or non-bonding orbitals also. So these orbitals are filled and the metal is empty. Then these filled orbitals, that is lowest non-bonding or bonding electron to the highest empty orbital of the metal, there will be a transition take place. That is called ligand to metal charge transfer. Charge transfer bands means a charge transferred from ligand to metal or metal to ligand. If the metal is empty or in a very low oxidation, high oxidation state, the charge transfer bands are possible because the ligand has a filled low-lying orbitals. Now, Another is metal to ligand charge transfer. Metal is filled and ligand as empty homoluma, you can say, highest occupied molecular orbital of the metal and lowest unoccupied orbital of the ligand. So there will be a transition from metal to ligand. This is called MLCT, metal to ligand charge transfer bands. These charge transfer bands are very, very high intense when compared to the DD transitions. So we can call it as a ligand centric. Sometimes we can also discuss about the ligand centric. As I told you, in organic ligands, we can have a pi, so bonds, n non-bonding electrons, pi star and sigma star. These various levels are there. If there is a transition from pi to pi star or isolated chromophores, you can say the pi to pi star or pi to sigma star. This is possible, but these transitions will take place not in the visible region, in the electron, in the UV region, because the energy is very high. So conjugated complexes, for example, there will be possibility of pi to pi star transitions, and compared to this, they are in a higher energy. As conjugation increases, the energy difference between the highest occupied field orbital and lowest occupied unfilled orbital decreases, and the intensity it takes place at higher lambda max, and intensity also increases. So just now we discussed metal to ligand and ligand to metal. So I also discussed here is the ligand to metal transition takes place when ligand orbitals, filled ligand orbitals are lowest in energy and empty metal orbitals are there. Then the transition from here to empty metal orbital. This is known as ligand to metal charge transfer transition. In some cases, what will happen is ligand has a pi orbitals and etc., where L2 sigma L2 metal may take place, pi L2 metal may take place. Okay, and in MLCT, what will happen is metal orbitals are low energy. Okay, like here, and pi star orbital of the ligand is empty and highest energy. Metal T2Z2, pi star, this carbon monoxide, etc. Ligands are pi star orbital. Then pi back bonding, that is what we call metal to filled d orbital or to empty pi star orbital. So these are ligands. So that's why, so NH3 sigma donor, SO3 2 minus sigma donor, F minus and Cl minus Br are pi donors, whereas carbon monoxide, cyanide, PR3, ASR3 is the pi acceptor ligands. They accept electrons from the metal filled orbital to the empty pi star orbital of the ligand, CO, Cn minus PR3, ASR3. That's why these are called pi acceptor ligands. We can also see pi donor ligands also, right? We have seen bromide and chloride, etc. So manganese, we discussed it. Mn4 minus is the purple. It has Mn7 D0. Oxygen has the non-bonding electrons. The non-bonding electrons, oxygen will go to the T2Z. So this is the ligand orbital. The transition is taking place. Sigma, that is ligand orbital to the T2Z orbitals of the metal. That's why it is a purple in color. Mercury sulfide also same thing. Reverse, that is metal to sulfur. So the transitions also takes place because I2 is an acceptor and this is a donor. Okay, and picric acid and this is an acceptor. This we discussed. This is about the what you call the F orbitals. So F orbitals also same SLJ's rule applies for the calculating the term symbols, that what we discussed just now. Okay. Same rule we apply. For example, this precision +3, the term symbol is, that is ground state term symbol is divided 6H15/2, right? We can calculate similarly what we have shown earlier, because all the ML as the removed electrons are there, +3, +2, +1, 0, -1, -2. So 5 unpaired electrons. So from this we will calculate this spin. Okay, sum of ML values. If you calculate the sum of ML values, it will confirm. Therefore, term symbol H like this we can calculate. So this is not necessary. Now to the LS coupling and JJ coupling. Okay, the LS coupling is more appropriate when spin orbit coupling is weaker in comparison to the inter-electronic repulsions. Okay, JJ coupling is important when spin orbit interaction is much stronger than the inter-electron interaction between the electrostatic interaction or inter-electron interaction. Now, so in the Russell-Sander coupling also we can calculate the J value similarly. Okay, only thing is what principle we use. Now we'll discuss the electronic spectroscopy of lanthanide +3 in comparison with the transition metal spectra. That means lanthanides, and that means 4F and 3D or 4D, what maybe transition metals and the electronic spectra. When you see the electronic transitions in lanthanides, so they are much weaker when compared to the electronic transitions of the transition metal 3D, etc. The reason here is the DD transition has produced metal compounds. These FFR both are forbidden. FFR also forbidden. So, but still DD transitions are comparatively more allowed than the 4F transition. The reason is 4F orbital is buried inside the 5s and the 5p, 4p orbitals. They're filled 5s and 4p orbitals are there. So the like d orbitals, the s orbital, there is no s orbital because any metal ion +2 metal ion, s is 0. So you have 3d1, 3d2, d orbital is exposed, whereas this is inside the core. So what will happen is, so whatever this relaxation that is possible, this vibranic coupling, etc., is in DD transitions. Because of the vibranic coupling, the symmetry is temporarily removed, and there will be a mixing of D and P orbitals. Okay, the DP, PD type character is observed, and it is giving some intense color when compared to the 4F transition. 4F, that is not possible. That's why the vibranic coupling is much weaker in lanthanides compared to the transition metal. That's why the color is very weak color, very light colored, we can see. So FF transitions are less intense because of the weak vibranic coupling, and lighter in color because delta 0 4F is greater than 3D0. Because when delta 0 is very high, in the beginning only we discussed it, when 3D to 4D, 4D to 5D. Similarly, when you go to the 4F and compared to D orbital, so the splitting is more. That means delta is more. If the delta is more, energy difference is more. That means the color which is absorbed is the blue end, and color which we appear is the red or yellow light. That's why when compared to the DD transitions, FF transitions are very lighter in color, and they're less intense. Intense in sense, the peak height is very high. Absorption is more, means more intense peak. Here less intense peak and very dull colors, light colors we can see. So the lack of 4F orbital and ligand interaction, those the FF transition energy of Ln3 plus ion change very little in its compounds, because like d orbitals, the ligand interactions are less in 4F orbitals. That's why, or sometimes no interaction with 4F orbital. That's why with the change of ligand, there is a lot of change in the spectra of the transition metal complexes, whereas change of ligand does not affect much the FF transitions in the metal complexes. So that's why, so these are the very weak transitions which we can see in electronic spectrum of. We can also see the spectrochemical series. So spectrochemical series is the order of arranging the what you call the ligand strength. Okay, for example, as the stronger that means strong field ligand means stronger the ligand, the delta zero is high. So such complexes will have more delta zero, and they can split the T2Z and EZ or T2 and E2 E very high. So that's why the spectra in this based on the delta zero, these ligands can be arranged in such a way the lowest delta zero is I value and follows, and highest delta zero is carbon monoxide. When you go this side, what is happening? Of course, I did also sometimes. These are the sigma donors as well as pi acceptors. That's why the bond formed is very strong, and the splitting is very high. That's why they stand at the right end in the spectrochemical series. So CO NH3 5 times NO2, yellow in color, it absorbs violet. CO NH3 5 times, it's coordinate through nitrogen, this coordinate through nitrito complex. O, so it's red color, blue color. Change in the coordination site also will affect the color of the system. Change of the ligand will also affect the color of the system. Now, the delta zero depends upon, as we discussed it, one is nature of metal ion, size of metal ion, and whether it is 3D or 4D or 5D, okay, within the metal ion, size of metal ion or metal difference in the metal ion. Oxidation state of metal ion. For example, Mn2 plus, it absorbs 7,800. MnH2O63 plus, this binds strongly because oxidation state increases, the ligand interaction will be stronger, so delta is higher, so this will absorb at higher wave numbers. Nature of the ligands will also helps. One is changing the delta zero, that's why. So stronger the ligand, we have seen in spectrochemical series, CO splits much stronger than the what you call the I minus. So that's why. So nature of the ligand, nature of the metal ion, and oxidation state of metals and nature of ligand will affect the delta, and in turn will affect the color of the transition metal complex. So we can also discuss some of the, because of the antellar distortions. That means this is possible only when, if you are talking about T2Z and EZ, and if the electrons in the EZ both are equally occupied, we don't expect any antellar transition, okay, distortion. If they are not occupied, what will happen during electronic transitions? If these two are not equal, one of the example T2Z and or EZ1, right? So the degeneracy will be removed when they are not equally occupied, because of this is occupied by one, this is occupied by one. What will happen is the one electron, the three orbitals, only one electron is occupied. Because of that, degeneracy will removed. One electron goes to the dxy. So among this one, the transition takes place now. Splitting takes place, and because of that, you can observe more transitions. Or so because of the antellar effect. So this is possible unsymmetrical distribution of electrons in the T2Z orbital and EZ orbital will remove the degeneracy, and because of removing the degeneracy, more number of transitions are possible. Or sometimes if transition more number is not visible, some overlapping may be occurred. If you observe the electron spectra of titanium complex, there is a certain degree of asymmetry of the peak, which may be due to antellar effect, because there is only one electron T2Z, right? So all T2Z electrons are not occupying the. So sometimes you will see the two bands. Sometimes you will see the distortion in the band structure. Okay, asymmetry in the peak. That tells that is because of the antellar distribution. That is nothing but whenever there is a unequal distribution of electrons in T2Z and in EZ, all three in T2Z or all two in EZ are not occupied equally, then this distortion takes place and more number of transitions possible. If they are not observed, what is possible is there is a distortion in the peak structure. So in extreme case, new bands will be observed. Okay, anti-LR effect is more, new bands will be observed. In other, splitting of peaks or an asymmetry of some peaks may be observed. This is about the peaks which we discussed. Then this already we discussed, not much. Student selection rule also discussed. Yeah, this we covered already. Okay, now that's what based on this, hydrated copper sulfate is blue color because it transmits, absorbs yellow color. Copper, ammonium sulfate, and sulfate is violet because it absorbs yellow, green light, yellow, green. That's why it's violet. That means the complementary color will be observed because in the beginning only we turned. When a compound or complex is interacted with visible light, partially some is absorbed, some is transmitted. The transmitted light is the color of that complex, right? If it is completely absorbed, it is black. If it is completely reflected, it is white. Anhydrated copper sulfate will not absorb when UV light, it is colorless. Hydrated copper sulfate only colored because anhydrated copper sulfate absorbs in higher region, whereas hydrated copper sulfate absorbs in UV visible region. Copper cyanide, it is also colorless because it is very strong ligand. The splitting is very high between T2G and EC, okay, or T2 and E. So what will happen is the UV visible region is not enough to take transition in the copper 9. So that's why, so UV region is needed. So when it absorbs UV, it is colorless. So there are some analytical applications of the one what we do in inorganic chemistry is physical rate constants, equilibrium constants can be determined, and only thing is when you are doing pK of the compound can be determined by using UV visible spectrophotometry. Okay, only thing is in two different pHs, one should be colored, the other should not be colored. So there should be change in the color change, either when ligand is added, metal is colorless and ligand should be colored, and metal ligand should be colored. In that case, you can, or metal is colored, ligand is colorless. When metal ligand complex is formed, the intensity might be increasing or intensity might be decreasing. Based on that, we can measure the equilibrium constant, rate constant, etc. On this equation, Anderson-Hertzsprung equation, we can determine the pK also. Not necessary. We can also mixture of two. For example, you have an anthracene and naphthalene. Two mixture is given because anthracene absorbs at 375, naphthalene absorbs at 355. So this mixture, you can estimate anthracene separately, naphthalene also, because you can measure the absorbance at 375, you will get the anthracene concentration, 355 naphthalene concentration, something like that. So you can, if there is a difference in the absorption of two different ligands, you can, for example, vitamin A and vitamin A2 also, A1 and A2, because they too absorb differently. So lambda max is at 325, lambda max is 351. So when you scan these two mixture at 325, lambda max, you can measure the concentration of vitamin A1 here. By using HPLC at 325, you can separate vitamin A1 from vitamin A2. So thank you very much for giving me the opportunity to talk something about the metal ion complexes, so the electronic spectra of transition metal complexes. I covered the DD transitions. I covered the metal ligand charge transfer and ligand to charge transfer. And I also covered charge transfer transitions within the ligands. We also discussed about the term symbols and Argel diagrams, etc. So thank you. Anything?
Thank you, sir. Thank you very much.
Yeah.
There are any questions? There are some faculty members also I could see. So if there are any questions, you can unmute and ask, students or faculty, anyone. ఎవరైనా అన్మ్యూట్ చేసుకొని అడగొచ్చు. మాట్లాడతారేమన్నా? ఫర్ 1 minute. Shukla bhai.
Yes, sir.
Yeah. Sir, you can unmute and speak, sir. Bhaiya.
Okay. Professor Satyanarayana garu.
Yeah.
Thanks a lot, sir, for you have thrown light on electronic spectrum of transition metals. Really, for the first time I am listening to this class, I enjoyed the class very much, sir. And I could learn something, sir. Thank you very much, sir.
Thank you.
And I appreciate the Kakatiya Government College, Ramesh bhai especially, and Principal Malesham garu, and Satyanarayana garu, Vasam brother Vatras, Vasam Srinivas garu, Sumalata, Vani,
Hello.
Ashok sir, Sunita, Mugli, and Janardhan Babu garu. All this were they are doing lot of work, sir, and their efforts must be appreciated. And on behalf of City College, I appreciate Balavaskar sir for giving this opportunity. And Yadaya sir, Dayanand sir, Vasanta, Busi, Anil, they are always with us. And this is for the first time, I think, with the interdepartment from different colleges, we have done this job. And this credit goes to Ramesh Babu sir for giving this opportunity. I thank from bottom of heart for this Vibranic levels as they synchronized, this could be happen, sir. Thanks for giving this opportunity. Hope this will continue in future. Thank you, Ramesh sir. Thank you, one and all.
Thank you, bhaiya. Satyam sir, Nara, Vasam. So once again, I thank. So thank you very much, sir. I also take this opportunity to thank our own principal, Dr. K. Malesham garu, is busy with some other assignment.
Yeah.
Dr. Balbaskar sir, and my colleagues, Satyam sir, Vasam Srinivas sir, Vani madam, Ashok sir, Sunita madam, Mugli sir, Jagdish sir, and City College faculty and friends, Dr. Shukla, Dr. Yadaya sir, Dr. Dayanand, Vasanta ma'am, and Anil Kumar, and all other faculty members who have participated, and also students of our college and other colleges. So once again, I thank you very much, sir, for sparing your valuable time and explaining in detail about the electronic spectra of metal complexes. So thank you very much.